All right, we're coming back. I have Kitty in my lap. He wanted to say hi. Probably to me. He probably doesn't recognize there are people watching right now. He is a very social kitty cat. This is Stuart. I just want you to recognize how big he is. This is like him against my body. He is a big cat. Anyway, hop down, Stu. All right. So with that, we are going to I'm not the Tiger King. I I maybe Cat King. I need to lose some teeth before I can claim that title. Anyway, let's go ahead and let's take a look at how the queue can be implemented. So with that, we have actually an implementation of queue, and this is actually already uploaded. So initially, we're going to say, okay, we have int current size, head, and tail. We're going to keep track of the current size. That's going to come up with grow if necessary a bit later. We set some initial size, in this case 4, but again, I could put any positive number here, even 1, and this could work. We initialize by creating our array of the initial size. We set current head and tail equal to 0. So, my cat bumped my camera while getting into his chair. He sits in my recliner. So, if let's say my queue were size 4, then I start by creating my queue of size 4. I set front and tail. That is first and last, so I'll actually abbreviate to F and L. F and L are both 0. We move L here. They're both equal to 0. Remember, they're not actually pointers, they're just ints, but we can think of them like pointers. That might help. We're also going to keep track of our size. Now, our size is not our capacity. Our capacity is 4. That's how many elements we can hold. Our size is how many of these cells are actually in use as part of our queue, and it's initially 0. From there, when we add to the queue, same as before, we have this grow if necessary. We'll talk about how that works later. But we add the element at the tail. Remember the tail being the first empty space. We increment our tail. And also, and actually this is a failing on my part that I don't have this, we need to increment current size as well. Current size plus plus. Now we'll talk about this if statement later, but we do need to keep track of the current size, so there we go. Now, let's illustrate this a couple of times. So I enqueue, let's say I enqueue, again, Shakespeare's, or Hamlet's soliloquy, excuse me. So 2, and then I increment last. So last is now 1. And then I do B. Last is now 2. Or, if I enqueue that, then last would become 3. And we'll stop there for now. So that is the simplest version of enqueue. There are some more complicated versions we'll take a look at in a second. From there, let's take a look at the code for moves, because so far we have not illustrated this if statement or grow if necessary, and we will illustrate both of those. From there, let's take a look at remove. So we're going to remove and then say head plus plus and then return the value we removed. So let's illustrate that a couple times. I forgot to update size. Size is now 3. Sorry, I did forget about size. So now I'm going to remove, and so I'm going to create a string out which is equal to 2. That is equal to this array's first value. And then I increment first. And as I said, I don't need to delete this value. I don't need to delete this value. Because if I get to it again, I'll overwrite it. And then I return out, and then I'm done. So now, let's demonstrate. Okay, so that's remove. That's the simplest version of remove. Let's demonstrate add again. So, to be or not 2. I add 2 at last. I then increment last. So, last is now 4. And, oh wait, that's out of bounds, isn't it? Well, in that case, I'm going to go back around, because remember, we think of these sides as connected. That is, the value after this one is the first value. So, I say last is 0. And the way that I can implement this is I can simply say, first I could do an if statement. If last equals the length of the array, then last equals 0. I could also, after I do L++, simply say L equals L mod 4, or length in this case. And if L was 4, well, 4 mod 4 is 0. So, I would get index 0. If L were anything less than 4, then L mod 4 would just be whatever L was. That's another way to think of it. We wrap around. Now, let's see, I had to be or not to be. So I would enqueue B again. So, how do I do that? I simply say, this array last is B, so notice that overwrites the 2, which I'm fine with. Then I increment last. And you'll notice something interesting here. And it is that last, this should be 1, last and first now point to the same value. When last and first point to the same value, there are 2 possibilities. The first possibility is that the 2 values are pointing to each other because the list is empty. The other is because they're pointing to the same value because the list is full. And the way we tell the difference is size. If size equals the length, then our queue is full. And now at this point, we can't add without growing. But are there any questions about anything I demonstrated so far? Just to show the code for this. Oh, and I forgot with remove, I need to do size minus minus. Important. Sorry, current size minus minus. Because I'm removing an element. Are there any questions about either of these 2 methods other than the grow if necessary part? Because we haven't talked about that yet. All right. So now let's talk about grow if necessary. So with grow if necessary, what I want to do is I want to double the size of my queue. So let's think of how we could do this. So if I want to double the size of my queue, then I need to create a queue of size 8. Two, three, four. 1, 2, 3, 4. So I create my queue of size 8. But in this case, I cannot simply copy the values down. Let's say I did. Remember that strings have a default value of null. So if I copied the values 0 to 0, 1 to 1, 2 to 2, 3 to 3, let's see what this would look like. Well, I would copy B, and 4, and not. And then my first and last would both be 1. Would this be correct? Or does anyone see a problem here? Does anyone see any problem? I just want to... This is how my cat sits. This is how he sits. I just want you to recognize that. But does anyone see a problem with this implementation? Well, here's the thing. If this is the first value of my Q, then the second value is OR. Then the third value is NOT. Then the fourth value is, we have a problem. What does the fourth value need to be? Can it be null? Is the fourth value null up in this queue? I have 23 viewers. I will wait till someone replies. Must be B, right? Well, no, we already have a new array. This is the new array, so I don't need to make another new array. That won't solve my problem. The problem is my new array is wrong. I would need to make sure that this B is not there, that this B is actually here. Because remember, the value after 2 needs to be B. Sorry, this B or... I'm missing the word not. Oh well, whatever. 2. B or not 2, sorry. I could do this. That is, this now copying index 1 to 1, index 2 to 2, index 3 to 3, and then index 0 to 4. Or I could actually just do the following. And this might be easier. And by the way, neither of these approaches is better. I'm just saying, which do you think is easier? What I could do is, instead of copying the values down that way, I could simply say, just take all the values out of here from first to last and put them in from 0 until I don't need any more values. So I start with the first value, and I say, okay, copy the first value into index 0. Then copy the next value, or then 2. Then the next value we wrap around B. And since our size was 4 values and we've copied 4 values, now we're done. And at this point, all I would say is first is always going to be 0 because I copied the first value into 0. And then last is going to be size. Last. This is index 4. And then I proceed as normal. The next time I add a value, I add it here, I increment last, and so on. And then from there, we just update our Q array to instead point to this array, ignoring this first one. This is grow if necessary. So let's illustrate that. So again, in the code, how does grow if necessary work? If the current size equals elements.length, why would last change? What do you mean? I'm not sure what you mean by last. Remember, last is the first empty space. Last and first wouldn't be the same thing anymore because our array is bigger. We have 4 more spaces. So last was always the place we would do our next insert. It was never the last value. Technically, it was the space after the last value. I guess I apologize. I'm not sure. Okay, I seem to have answered your question, I guess. Okay. Why wasn't autofill null a concern in stack? So the reason is, with a stack, the reason this didn't come into play with a stack is effectively what we were doing was we were taking our stack. So let's say our stack were something like 5, 7, 3, and we're copying it to this stack. Now, we don't need to change because the bottom is always 0. We can copy the values over. And now notice we can put values onto the stack here. We're just going to overwrite the null and the null and the null. Because the issue is we didn't have to worry about the first ever moving. The first value was never going to move. It's always going to be 0. So we can always just add on. We can't copy the array contents over in the same way here, because remember, this b is not the first value. It's the last value. This b is the first value. So our first value is not necessarily at index 0, which means if say our first value were this index and our last value were below it, and we added 3 empty spaces, then our stack in order would be 7 5 null 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 3. That's what would have happened. So we don't have to ever worry about that with a stack because our first value is always null. So I copy from first to last rather than from 0 to length. That's the key. Because the order b or to b has to be preserved in the new array. The queue's order can't change just because we grew it in size. In fact, it very much needs to not change. Otherwise, it's not functioning correctly as a queue. Because the point is, if I do 4 removes, no matter how many values I add, my next 4 removes should say b or to b, no matter what. No matter how many values I add. Any questions? All right. So then from there, we just simply wait, no matter how many values you add. Yes, so like if I added 100 values, I would call grow if necessary multiple times as a result of that. But the first 4 values on my queue, if 100 people get behind me in line at the movie theater, my position hasn't changed. Right? Like if I add 100 words here, this is where I'm going to add the first word, the second word, the third word, the fourth word. And then I'll grow if necessary, and then the 5th, 6th, 7th, and so on. But this is still my first value until I call remove. This is still my second value until I call remove. This is my third until I call remove, my fourth until I call remove. And so you only ever move forward in the line. If people get in line behind you, that shouldn't make you take longer. Right? That's the idea. All right. Hang on 1 second here. Let's see. Okay. All right. Any questions? So it's like I don't know if it's the opposite of it. I guess it's kind of the opposite of stack. Like last in first out is the opposite of first in last out. But opposite's such a weird term because if is a cold night the opposite of a hot day, or is a cold day the opposite of a hot day? Is that double negative? I don't know. So it gets weird at that point. I would just say that they are diametrically opposed in that queues are first in first out, and stacks are first in last out. Anyway, you wouldn't be happy if you went to a restaurant and they implemented their wait system like a queue, because then people who arrived after you would get a table before you, which wouldn't be something that would make people happy. All right. From there, let's just quickly add some values to queues. So I add, and then I print, and then I remove, and then I print, and then so let's just run this real quick. And you'll see that when I print the queue, this time I set it up to print the null values, but I also print head at where the head is and t at where the tail is. And so you can see that after I add the first value, the head is 0, the tail is 1. After I remove, the head and tail are both there. But the key is once I wrap back around, so if I add another value, my add e, it will simply just overwrite. It will simply just overwrite that value a, And now my tail is there. And if I add a couple more values, and I'm just going to add a couple values before I print again. F and then G. And then I print the Q. You'll see that now it has grown. And now I have still, the head is C, right? The head is still C. The head value hasn't changed. It goes C, D, E, F, G, and then the nulls after that. Camera is on top of the console. There we go. That's the illustration. So before I add F and G, I have the order C, D, and then E. B has been removed, so while it's still here, it's not really part of the queue. It doesn't really matter what this is because the tail is going to overwrite it when I add. So when I add F, it overwrites that B. And then because I'm out of space, I grow, and you can see what happens here. Any questions about a queue? And again, this is an implementation of a queue. This is an implementation that would be referred to as a ring buffer. So that's a useful term to be familiar with. The idea is rather than think of the array like a line, you think of it more like a clock. Right? Like, it's not, the clock doesn't end after 12 o'clock. It cycles back to 1. It's the same idea. It's worth remembering that term because it will come up again. But this is an implementation of a queue, not the implementation. There is no the implementation. A queue is abstract. And by the way, this code's uploaded, so that makes, other than the typos, which I'll re-upload this submission since I fixed a couple things. Other than that, that's basically the daily activity. So it's pretty easy today. Any questions about stacks or queues before we move on to talking about algorithms? All right. Algorithms. So the goal for this unit is we want to talk about data structures and algorithms from a standpoint of efficiency. And we talk about algorithms from a nature of performance. And that performance, we mostly talk about time, how long an algorithm takes to run. There's other relevant factors, like for instance, how much memory the algorithm takes. We want an algorithm to be as fast as possible while using as little memory as possible. We often call memory space because in order to store memory, you need physical space to do that. It requires physical hardware to store information. So that does take up space. So I want to be clear that we're just giving you the briefest of introductions here. This material is much more heavily iterated on and expanded in 2150 and 4102. I am giving you the bare bones foundation, the foundational expectation that you have, and then you will build on that in later courses. So I do want to be clear about the nature of that. So first, what is an algorithm? An algorithm is a detailed step-by-step method to solve a problem. Code is a computer algorithm, but an algorithm does not require a computer. A recipe, a cooking recipe, could be called an algorithm. The key for an algorithm: the steps need to be precisely stated such that there is no ambiguity. They cannot be misinterpreted or interpreted multiple ways. They are deterministic. If I have the same input, the same state, then I will always produce the same output. Now you may be thinking, okay, so they can't be random, right? This is where it gets a bit murky, but like the math.random that we used is not actually random. It is deterministic. If I had the exact same state of my computer with the exact same time and I managed to use time travel such that my system clock were exactly the same, I would always get the same random number. It's just because I'm constantly moving through time and I can't stop myself. Um, there's an XKCD comic of all the dimensions to be inexorably pushed forward through. Time is better than, say, up, for example. Um, but I can't repeat that experiment, but that is to say Math.Random is deterministic. If you had managed to pause the universe and kind of split two parallel universes and ran Math.Random in both, you would get the same thing. It terminates, which is to say it has to end at some point. There's other properties like correctness, generality, efficiency. These are kind of qualities that we say how good an algorithm is. But it's required that an algorithm be a precisely stated step-by-step set of instructions, that it be deterministic, and that it terminates. Which, if we look at this code, it is precisely stated, step-by-step instructions. It terminates when we reach this closing bracket. The steps can't be misinterpreted. So this is an algorithm, but an algorithm doesn't require a programming language. Any questions? So the key is that some algorithms are better than others. I want to illustrate this. I have uploaded to the course website something called where is it? List analysis. And this program is fairly straightforward. What it does is I create two different lists. I create an array list and a linked list. And I just, it kind of think of this like doing a time trial. So how do you compare two cars? You go out to a track, both cars drive a lap, you time them. Whoever lap time is shorter, that's the better car, right? That's exactly what I'm doing here, except instead of cars, I'm using lists, and instead of a racetrack, I'm doing several different features within a list. So for example, the first thing I do is I try inserting at the end of the list. And I want to see which is faster. Is it faster to insert at the end of an array list or at the end of a linked list? Which is faster? From there, I clear both lists. That is to say, I empty them. And then I try adding, and by the way, I do 100,000 values. So this is a very, a large number of values. The point being, if there's any discrepancies, the very large number of tests I do will do that. And you can look at the code to see how it's implemented. It is uploaded, but I just want you to understand, I'm doing 100,000 adds at the end on both the array list and the linked list. Then I empty it and I insert at this is actually the beginning, at the front. And we'll see which is faster, linked list or array list. Then I clear both, and I pick a random position in the middle. So I use a random number generator to pick an index between 0 and the length of the array list or linked list, and I insert it there. Finally, I try to access the 1,000 random elements. So I get the 500th element, or the 4,732nd element, whatever. I randomize a number, I pick that element. Let's see, given this experiment, which type of list is faster. I know we don't really know how the linked list works yet, but let's just try to see which is faster. So right out of the gate, you can see both arrays adding at the end were very fast. In fact, this 0.004 difference is negligible. It's actually more attributed to the startup than it is attributed to the algorithm. Whereas adding at the end of a list, you can see linked list is quite a bit faster. Adding to the end of an array list took nearly 0.4 of a second versus 5 thousandths. I mean, this is a big difference. This is almost 100 magnitude difference, right? But then when I insert in the middle, wow, array list, about an eighth of a second, maybe a little bit more than a sixth of a second, actually. A little bit more than a sixth of a second versus 14.2 seconds. So adding to the middle of a linked list is insanely slow. Much slower than any of the other steps we've done. If I get 1,000 elements, going back to the code, or randomly access 1,000 elements in an array list, it doesn't even register as taking any time. It's just that fast. It literally took less than a millisecond, which is the timing interval I'm using. The linked list took a third of a second. So the point is, from this experiment, what we can gather, some broad understandings, just from testing this, from running these two things, is both are fast at adding to the end. Both are fast at that. Or linked list are much faster at adding to the front. Adding to the front than array lists. But array lists are much faster adding to the middle. And the general difference that we find, the general difference that we find here is that array lists are better when you need to add elements into the middle or access values in the middle of the list. Linked lists are better when you will only add or remove from the front back. If you're only adding and removing from the front and the back, linked lists are better. If you're doing anything in the middle, array lists are better. Now how we determine that, we'll talk about. But I just want to say that we can experiment with algorithms and determine which is better. And we define better as performing the same number of operations in a shorter amount of time. Both of these are lists. We have the abstract operation, add to the end. We have the abstract operation, add to the front. We have the abstract operation, add somewhere in the middle. But how they work in an array list and a linked list, they actually do very, very different things. Are there any questions about this? This is broadly how we analyze algorithms. We think of them in terms of we want faster algorithms that use less memory. Although, all things being equal, time is more important. Now, we do care about time, and we can do these experiments to get empirical times. But here's the problem. I bet if most of you ran this, it would probably run slower. I'm pretty proud of this baby. I built it myself. I quite indulged. Some of you will probably have better computers, but it's a really good computer. It's a gaming computer. It can do a lot. Your laptops, if you have laptops, probably will not run anywhere close to this fast. Might be a lot slower, especially if it's an older laptop. Might be faster, but it might be slower. Depends a lot on your processor. The point is, this is subjective to your computer. And if I took this same program and ran it on a computer 10 years ago, it would be dramatically slower. So time is actually not a good measure because it's constantly changing. There's a great thought experiment, and the thought experiment is, let's say that we continue to build spacecraft that can go faster and faster and faster and faster. Let's say that right now we could build a spacecraft that would travel to Alpha Centauri, the nearest star, 4 light years away. Based on our fastest technology, it would take something like 1,000 years to get there. If we wait 100 years, we might have technology that the the ship can get there in only 500 years. So by waiting 100 years before we start, we can actually cut 400 years off the time it takes to get to Alpha Centauri. And if we wait longer, our technology might be even better. And there's some point where it optimizes. Now, we're not talking about optimizing computers. The key thought experiment here is the time to run changes. So we need some way to measure the efficiency of an algorithm that takes into account time, but is not an exact measure of time. So what we want to focus not on how long it takes something to complete, but how fast that rate of completion grows as the problem gets more complex. Here's what I mean by this. When you add to an array list, here is what happens. When I add to an array list, what happens is the following. If I add to the end, let's say my array list looks something like 5, 3, 7, and I add 4 to the end, it just adds 4 back here. And then it would add 2, etc. But if I add to the front, and yes, there's the grow if necessary thing, but don't worry about that because as I talked about, it averages out in the wash. But if I add to the front, before I add the value, I have to shift everything over. So I have to shift over 4, then 7, then 3, then 5. You don't have to do this shifting in a linked list, which is why adding to the front of a linked list is faster. And then I can add the value 2. So the number of steps I need to do is I need to move the size of my array and then add 1 value. So if my array were size 100, before I call the add, I would need to move 100 values. That takes 100 steps. And then I would need to insert the new value, plus 1. That's 101 steps. Here is what we mean by increasing the complexity of the problem. What if I double the size of this input? What if instead of moving 100 values, I have to move 200 values? How many steps does this now take? How many steps would this now take if I have 200 values to move instead? Anyone? $201, right? Because I now have to move 200 values. And if I and so now this becomes 201. So by doubling the input, doubling the size of my array list, inserting at the front takes double the amount of time. So whenever so we can think of if I double the size of the problem and the runtime doubles, we have a word for that. If I double the size of the problem and it doubles the runtime, we call this a linear rate of growth. Linear. And that's because if I were to make a graph of the runtime as the array got larger, that graph would look like a linear graph. It would look like a straight line. And it would grow at exactly the same rate as the input grows. But now, let's consider adding to the end of an array list. And let's say we don't have to worry about grow if necessary at all. I know I'm kind of hand-waving on that, but just trust me. Let's say we don't have to worry about grow if necessary. If I just need to add to the end, and I have space for it, it doesn't matter how many elements I have. Because here is how I add. This is where I'm currently going to add. I add it, and I move this index. And then I add a value, move the index. If I don't have to worry about grow if necessary, this always takes 2 steps. I add the value, and I increment my end pointer. Therefore, it doesn't matter if this array, or excuse me, if the size of my array when I call add at the end is 100 or 200 or 1,000. No matter how big the problem is, it takes the same number of steps. Again, kind of hand waving on growth necessary, don't worry about it. So the way we implemented our stack and queue were to follow this. It doesn't matter how big our stack and queue get, it always takes the same number of steps to add or remove values. And that is called constant time. Because it doesn't matter how large, I just realized that's kind of covered up. I'll write it down here, constant. It doesn't matter how large the problem gets, it always takes the same amount of time to solve. An example of this would be getting the first value of an array. Same number of steps, but takes longer. No. Takes the, again, with a constant time operation, it takes the same amount of time because these steps are running on the same computer. So no, it doesn't take longer. Like getting the value of the first value of an array list, it doesn't matter if the array list is size 1 or size 1 million. It always takes the same amount of time. Getting the last value of an array of size 1 or 1 million always takes the same amount of time. So a constant size problem is one where the runtime is not expected to change as the problem's complexity increases. So it does not take longer. So if I were to map constant time, graph it, it would look something like this. It would look like a horizontal line. Even as the problem gets bigger, the runtime doesn't change. Now, from there are more classes, but let's start with that. So adding to the front of an array list is linear, but adding to the end is constant time. With a linked list, they're actually both constant time. And we're not going to talk about why today, but just put that in the back of your mind. So how do we compare algorithm efficiency? Well, we compare it by comparing data structures. We don't compare abstract data structures. I don't compare adding a list to adding to a set because they have different purposes, and also a list and a set are not implementations. I can compare an array list to a hash set for operations they share in common, but I can't compare like array lists and hash sets on things they don't have in common. But so we compare structure, we compare algorithms as defined in the concrete. So you could write your own queue implementation and compare it to this queue implementation, the specific one I wrote here, but you can't compare it to the idea of a queue. Because abstract things don't have runtimes. Only concrete things have runtimes. And so, again, an ADT can be implemented as either an array list or a linked list. These are better at different things. Array lists are better in most situations. Linked lists are better in some narrow situations. So, from there, let's consider the efficiency of the remove method of an array list. How do we define the efficiency? Well, we can if you actually compare these, it turns out that remove on a linked list, if you're removing from the front or the back, is if you're removing from the front, I should say, is faster than an array list. Whereas removing from the back, they're about the same. So again, like, we can't compare the actual runtime. You running your algorithm on your computer can't be compared to me running my algorithm on my computer. Like, if you have a MacBook and I have this, and someone else has a Raspberry Pi with an ARM processor, these are all going to run the same algorithm in different times. So when we're comparing algorithms, we don't compare runtime on different machines. So we need a way to analyze algorithm that doesn't actually require timing it. That's the key takeaway. How do we examine algorithm runtime without using a stopwatch? Now, time, again, is not the only thing we care about. It tends to be the most interesting. We do care about memory as well. But usually the runtime of something is dependent on the size of the input. sometimes dependent on the nature of the input, but it's usually, almost always, dependent on the size of the input. That is, the larger input that your program needs to take in, the longer it will take. I'll give you an example. If I were to calculate the average grade on the exam in the class this summer by hand, that would take significantly less time than it would have taken me in the spring to do the same. Why? Because in the spring I had almost 600 students, 574. This summer I think I'm at 38 active students right now. So, adding each student, let's say that would take some unit of time, whether that's a second or half a second's irrelevant. Some unit of time. Well, the number of students I have, that's how many numbers I have to add. There's no shortcut. That is linear. And because my class is larger in the fall and spring, it therefore would take longer to perform that process because the input were larger. So we often measure efficiency by counting the number of steps. We think about steps, and we define these generally fairly fast and loose. But we can define this as time is some function of n, where n is the size of the input. So going back to my problem from before, let's say I were averaging the grades of all students. In the spring, my n was 574, the number of students I have. That is my n. But in the summer, it's 38, which is also my n. That value is still called n. It's the size of the input. And we express things as a relationship from size to runtime, or some function of n. So we're going to throw out a little math here. Some function of n. And we do that by counting the steps. And it turns out that we actually don't care about defining a precise function. We care about describing the order of magnitude of the function. We'll talk about that in a second. So, one example often is choose one particular operation that is likely to occur over and over and over. Choose one particular operation or section of code to count, and count how many times that runs. And we want to count the critical section. What do I mean by a critical section? A critical section is the part of the algorithm that gets repeated the most. For example, here in the function print q. Printing the q is obviously, it's trivially linear. If I double the size of the queue, I have to print twice as many things, right? Hopefully that makes sense. The reason I can map that out in code is I can look at this section of code and I can say, okay, here is a loop. This is looping from 0 to the number of elements I have, elements.length. Well, the number of elements I have is the size of my input. It is n. And I am doing each of these steps n times. So I am doing 1, 2, 3, 4 steps n times. This loop iterates n times. So you could think of that in terms of print q. You could think of this as f of n equals 4 times n, because this loop runs n times and contains 4 statements. Plus, I have this one statement before the loop and this one after. Sorry, this one after. So those both take 1 step. So you could think of that as plus 2. Now, one line of code is not always 1 step. We'll look at some practical examples of that later. In fact, almost never is one line of code actually 1 step. We're playing very, very fast and loose with the definition of step here. For instance, you could argue this is 2 steps. The first step checks if this statement is true. The second step is, if it's true, you perform this add. We're going to play fast and loose with that definition. There's not a big difference between 2 and 1 step. There is a big difference between 1 and n steps, because n could be any number. It could be very large. So it turns out that broadly, we don't actually care about the 4 or the 2 here. And here's why. Remember what I said before. If an algorithm is linear, then when I double the size of the input, the runtime doubles. Let's assume for a second that this were an accurate measurement of the number of clock cycles it took for this algorithm to run. Let's just assume it were accurate. If it were accurate, this statement holds true. For example, if n were to be equal to 1,000, then f of n is 4,002. Or I could just write this as saying f of 1,000 equals 4,002, because 4 times 1,000 is 4,000 plus 2. If I double the size of the input, so now it's f of 2,000, 4 times 2,000 is 8,000, plus 2 is 8,002. This is roughly, not exactly, but roughly double. And in fact, as n gets larger, this gets closer and closer to double. So we don't actually care. I know that sounds weird. We don't care too much about the 4. We mostly care about the n. And we'll do some more mathematical notation on this tomorrow. But are there any questions so far about what I mean by linear? And why this algorithm is linear time? And again, this seems straightforward because, of course, if I'm printing a queue, if I'm iterating through a queue, printing every element, obviously it's going to take visiting every element or some function of n steps. How did you determine 4 and 2? I had 4 lines of code inside the for loop, which runs n times. So that's 4 times n. I have 2 statements outside of the for loop, 1 and 2. Now, are these all exactly 1 clock cycle? No, they're not. But again, the point is, it actually doesn't matter. If I change this number to 37, if I made that 37, this statement would still be true. And if I made this value 15, this statement would still be true. I'll say roughly doubles. Now, not all algorithms are like this. Some algorithms, for example, may take f. So let's actually look at remove. Remove, notice there's no loop. We have 1 step, 2 steps. We can call this 3 or 4 steps. We'll call it 4. 5 steps, 6 steps. Right? Remove from my queue takes 6 steps. So f of n equals 6. Notice n is not part of this definition. There's no loop. There's no line of code that runs the number of elements I have times. Right? This always takes 6 statements to execute. So f of 1,000 equals 6 and f of 2,000 equals 6. It doesn't matter. So generally, if a function has no loops, then that function is constant time. And we would love it if everything we wanted to do in computer science could be done in constant time. That would be so fantastic. It's not possible. For instance, there is no way to implement printing this queue in constant time. There's no way to do it. Because the queue's size varies. It varies as a function of n. And the longer the queue is, the longer it takes to print. Because you have to generate each character as you print the queue. So some things cannot be implemented faster than a certain maximum efficiency. If I want to get the average grade of students in the class, and I do that by adding up every student's score, there is no way to do that faster than linear time. It will take a linear number of steps. So there are some algorithms that cannot be improved upon. The worst algorithms are exponential. And oftentimes, I will see someone look at a function that looks like this. X squared plus 2x plus 1. And they will say, oh, look, this function is exponential. No, it's not. This is not exponential. Exponential, very specifically, is when it's some f of n is some constant. Sorry, these should all be n's, not x's. Is some constant a raised to the power of n. And there are things that, near as we can tell, do not have anything better than exponential. Right, this is called quadratic. More broadly, we would describe it as polynomic, or that is to say, the function can be defined by a polynomial. And we'll talk about how there's different polynomial groups that we care about. Like, we care uniquely about quadratic and a few others. But exponential algorithms are really, really, really bad. And there are some things out there, like the knapsack problem, that our only solutions we are aware of are exponential. What about x to the 1 over n? I'm not familiar with any algorithm that could be implemented like that. If you could find an algorithm where that is the runtime, I'd be very interested to see it. So you can't just use logarithms, though. You can't just make an algorithm be, take log time. There are log algorithms, and we'll talk about those here in a second. But I just want you to know that if you ever hear something referred to as exponential, this is what it means. This is actually why, if you want to pay attention to a disease, pay attention to the rate of infection. The rate of infection is typically, for every one person who gets sick, n people get infected. And if this n is greater than 1, that means the disease will grow exponentially. For example, let's say the rate of infection were 2. So we start with one person, they infect 2 people, now 3 people are infected. Those 2 new people infect 4 people, now 7 are infected. And then 15. And then so on. Exactly. No, that's exactly the case. This is why, for example, when places open up, it's going to expand. I mean, that's happening in Florida, it's happening in other states. I hate to tell you that. That's going to happen everywhere. I mean, the reality is, I'm just telling you this now, the reality is don't expect normalcy within the next year, year and a half, 2 years. I mean, just until we have a widely distributed vaccine that people can have, don't expect normalcy. I am a diehard college sports fan. I want, with every fiber of my being, to have college football this fall. I'm looking forward to it. I fully expect it will not happen. We may have, like, half the games played, if that. Because, I mean, right now, we're hitting new records. The point is, that's what exponential growth does. There's a cool video I'm going to link in chat. You can watch on your own time to give you an understanding of exponential growth. This is actually my favorite video to demonstrate exponential growth. I should also note, it is kind of depressing and sad. It's not Plague Inc., it's Minecraft. It is a Minecraft video where a guy demonstrates exponential growth as a factor of time. I do encourage you to watch it when you get the chance. But so when we talk about algorithms, what we care about then is not the runtime. Focus on rate of growth. That is, if I double the size of the problem, how much longer does the problem take to solve? If it's constant time, it doesn't take any longer. Same. If it's linear, that should be constant. If it's linear, doubling the size of the input doubles the runtime. If it's quadratic, it quadruples. If it's cubic, it octuples. If it's exponential, well, it depends on what the base is. Let's say it's exponential 2 to the power of n, like the naive solution to the knapsack problem. This squares the runtime. That is, if the runtime took 100 seconds, it will take 10,000 seconds because you doubled the runtime. Does Minecraft use stacks? I mean, it's in Java, so it uses the stack. So we'll talk about these groups and examples of them tomorrow, but just remember to keep in mind as you do the reading. With algorithms, we focus on the rate of growth. We don't care about the exact runtime. We actually don't care because the exact runtime will change. You want your program to run twice as fast? Wait 18 months. Right? Moore's Law doesn't really work that way, but the point being, wait some time, your program will run faster. We're not interested in exactly how fast a program runs. We are interested in, if we increase the input size, how much longer does the program take to run? Will we have to decipher the formula by looking at a snippet of code on the final? Probably. Sounds like something I would do. I mean, I never promise that a particular question will be on the final, but that sounds like something I would do. Java demonstration Minecraft. Minecraft code has... I used an early version one time, and I manipulated some variables to show students what would happen. But that was a very early version that was open source. I think it technically was bootleg. Maybe it was the... Anyway, Minecraft is not open source. So, yeah. Technically, I now that I have, because at that time I had 30 students. Now that I have like potentially 600 students, I think technically that falls under either piracy or DMCA or both. And I don't want to do either within my job. So we'll wrap up class here for today. So just to let you know where we're going to pick up, we will pick up by talking about asymptotic analysis. Is there a computer program tell you the complexity of a program? No. No, there is not. And if there were, I wouldn't tell you, because then you would use that instead of learning how to do it yourself. But no, there isn't. There can't be because of something called the halting problem. There is no program that can tell you whether or not your program will finish executing. That is the Church-Turing thesis. Well, one of the many parts of it. There is no program that will tell you that your program will even terminate. Therefore, it can't tell you the runtime. Sorry about that. Luckily, that is cut off the top of the screen. Anyway, I didn't want people to see my Steam profile name, no offense. Alright, so we'll pick up there tomorrow. And remember, homework 2 due tonight. Homework 3 has been released. The webcat is up for that. Homework, it is due Thursday, but it is a much shorter assignment than homework 2. With that, I'll see everyone tomorrow. Take care.